Now let us talk about nuclear power stations. So obviously in nuclear power station you use heat energy which is released from nuclear fission, and you use that heat energy to produce steam, which rotates the steam turbine, which in turn rotates generators which produce electrical energy. So let us look into these plants in detail. So first of all, we can define nuclear fission. We have already defined nuclear fission and we have studied it previously, but let's revise that. So any heavy radioactive element like uranium or thorium, that can be broken up into smaller elements, and when it breaks up into smaller elements, it releases a huge amount of heat energy in the process. So this process is called nuclear fission. It happens spontaneously in environment as well, but in a nuclear power plant we make it happen by creating conductive by facilitating this process. So normally in a coal-fired power plant, coal combustion happens in a boiler. But in a nuclear power plant, fission process, which generates the desired heat energy, it happens in a unit which is called a reactor. So in nuclear power plant, there is no boiler, there is a reactor. While in a coal-fired power plant, that same thing which produces heat is called a boiler, not a reactor. So heat energy converts water into steam and that runs the steam turbine. We have already seen that this heat produced by complete fission of 1 kilogram of U-235 is the same as that produced by 4,500 tons of high grade coal, that is anthracite. So a huge amount of heat energy is produced, and so the sizes of these nuclear power plants are lower as compared to steam power plant, corresponding steam power plants. Now let us look at the advantages. So first of all, we have low fuel requirements. Obviously, a small quantity of fuel can generate a lot of power. The space requirements are obviously less. Then there are very low running charges, very economical for producing bulk electricity. This is very important advantage, as the nuclear power plants, they cannot they cannot vary their electricity production very easily, obviously because the fission reaction has to be altered and that is not a very advisable thing to do. So normally these power plants work at a constant power and they produce power constantly at that level, and they are used to produce bulk electricity. So obviously their fuel supply is inexhaustible, and it is available for thousands of years. So the disadvantages of this technique is that the fuel obviously is expensive. It is difficult to recover. Once it has been consumed, you cannot recreate U-235 very easily. So the capital costs involved with the plant are high, obviously because you have to shield against radiations emitted from the plant. You need technically experienced staff to commission the plant and to operate this plant, and radioactive pollution is produced because the waste which is produced by the plant, once the fuel is spent up, it is used completely, then that is radioactive waste, and that generates radioactive pollution even if it is disposed of properly. It is not suitable for variable load requirements, obviously because for very fine adjustments you cannot vary the output of the plant that much. So, if you want to see the statistics on the evolution of nuclear power in Pakistan, they can be found at this link, and I encourage you to go over there and look at the history of development of nuclear power in Pakistan. And it is quite shocking, but you can see it in that website. So this diagram shows the basic principle of operation of a nuclear power plant. So what happens is that you have a nuclear reactor, and then in this nuclear reactor fission is happening and a lot of heat energy is being produced inside this nuclear reactor. So this heat energy has to be removed from this reactor, but you cannot use ordinary water to do that because it will not be able to handle that temperatures. So what you do is the water is we cannot design a system for economically for water to handle that temperature. I will explain on this point if you ask the question in QA sessions. So cold metal, which is normally sodium or sodium potassium, is flowing into these pipes because of this pump, and this pump pumps this cold metal via a filter into the nuclear reactor. This cold metal then flows inside between the rods of the fuel rods and the arrangement of the nuclear reactor, and it gains up all of the heat energy which is produced in the inside the reactor, and then hot metal escapes the nuclear reactor. This hot metal is then allowed to enter a heat exchanger in which it flows inside the pipe, and water is also injected from a water source, which is maybe a river, via a circulating water pump and a feed water pump, and it is injected into this heat exchanger, and it removes heat energy from this hot metal, again making it cold. And this heat energy then converts this water into steam, which is directed into the turbine via a valve. The valve controls the amount of steam entering the turbine, and thereby controlling the speed of the turbine. So the turbine in turn is coupled to an alternator which produces electricity, which is fed into the grid via transformers, and several protection devices are also inside here, like circuit breakers and isolators. Their objective is just to isolate the plant in case of any faults. And then there is an exciter system which is for the synchronous generator, and it creates the permanent magnet of the synchronous generator. So the exhaust steam from the turbine is fed into the condenser, where it is condensed via, via the cooling tower. This condensed steam, which is now water, is again cooled and then circulated again, added into the feed water pump supply. So this right here in these figures, you can see the 137 megawatt Karachi nuclear power plant, Canoe, with CANDU reactors, and this plant is undergoing capacity extension, and after this capacity extension, this plant will be capable of producing 2200 megawatts or 2.2 gigawatts of power. Just as a reference, right now it is capable of producing 137 megawatts of power, so it is a very low power production, but this extension is expected to be completed by 2022, and it is being done by a Chinese firm. And after this extension, this power plant will be capable of producing around 2200 megawatts of power. So now let us talk about a chain reaction which happens inside the nuclear power plant. So when a slowly moving neutron is directed at nucleus of a uranium atom, this neutron hits the uranium nuclei, and it gets absorbed into the nucleus of the uranium atom. This makes the uranium atom unstable, and the uranium atom splits into smaller stable elements, and this process releases a lot of heat energy, and obviously some more neutrons are also emitted. Each uranium atom is capable of generating 2 neutrons per fission. So combined with the incident neutron, the total of 3 neutrons are generated after every fission. So these 3 neutrons are generated after a fission, and our goal is to allow only one of these 3 neutrons to further strike another uranium atom, thereby producing another fission. Why is this our goal? Because if we allow more than one neutrons, first of all, if we achieve this goal, then a sustained reaction takes place, like the reaction keeps on continuing without outside interference, and this sustained reaction is termed as chain reaction. So if why it is necessary to only allow one neutron to strike further cause another fission? So that is important, because if more than one neutrons strike more than one uranium atoms after any fission, then the reaction rate will keep on compounding. It will keep on compounding, it will go out of control, and that will cause a lot of heat energy production inside the reactor, which will obviously go beyond the design limits of the reactor and will cause the reactor to explode. So it is extremely important to only allow one neutron from a fission to then further go on and perform another fission. More than one, if more than one neutrons are allowed, then the reaction will go out of control. Now let us talk about a nuclear reactor. So the nuclear reactor is any place where chain reaction is happening, and inside which the chain reaction is happening, and we are controlling the chain reaction by elements of a nuclear reactor. So normally it is a cylindrical and stout, very strong and thick pressure vessel, and it houses fuel rods, control rods, and moderator. Now I'm going to explain these things in a bit. So fuel rods are normally made up of uranium pellets. Normally they are small pellets of uranium, and they are all combined into a fuel rod. These fuel rods are made up of uranium pellets, while the control rods are made up of cadmium or boron, and they keep the rate of reaction in check. These cadmium and boron rods are there to control the number of neutrons which cause further fission. So these control rods are in fact controlling the rate of fission inside the nuclear reactor, and they are very important. Abrupt control of these rods can cause instability of reactor, and it can cause the reactor to explode. So they are very important portion of a reactor. So moderator is anything which slows down the neutrons, because if a neutron is moving too fast, it will strike a nucleus of uranium and it will go through it. It will not be absorbed inside it. That will not cause fission. And if it is too slow, it may not be able to it will not be able to even make it to the uranium. It will not be able to cause fission. So it is at an appropriate speed. It is the speed is neither too high nor too low, and this neutron, when it strikes the uranium, it gets absorbed in it, and that is achieved by use of a moderator. So when the control rods are lowered into the reactors, more neutrons get absorbed in these control rods, thereby reducing the rate of fission reaction. The fission slows down, and if you keep these control rods lowered, then the fission process will eventually stop, as the reaction will not be able to sustain itself any further. So if you take these control rods out of the reactors, then the rate of reaction increases, and we control the chain reaction via control of these control rods. So how much power we have to produce depends on how much fuel rods are there in the nuclear reactor, and then the number of control rods which are present inside the reactor determine how much is the rate of reaction and how much power is being produced. So that is what I meant. You can just visualize. You cannot use this plant for very fine adjustments of the power generation, and so you can only produce power in bulk with these reactors. So the control is not that easy. So there, the coolant is a in the previous figure we saw the coolant which moves inside the reactor and collects all of the heat energy and then flows outside the reactor, and then in the heat exchanger it exchanges this heat energy with the water and converts the water into steam. So the coolant is sodium metal normally, and it is circulated through the reactor to remove the generated heat from reactor, and it carries it to the heat exchanger. So heat is transferred in the heat exchanger to water, thereby converting it into steam, and then that runs the steam turbine and produces electricity via generators. This is the diagram of a nuclear reactor, and in this diagram you can see that this is the reactor. Over here we can see the reactor, and then this right here, this is the moderator, which is graphite in this case. This slows down the neutrons which are striking the fuel rods, and then these are the black ones are the fuel rods, and then we have some control rods which we can lower into the reactor to control the rate of the reaction. The coolant is is made to flow by coolant circulating pump, and this coolant is flowing into this pressure vessel, and then it removes all of the heat energy inside this pressure vessel, and then it flows out of that vessel via these pipes, around which we have water, which is injected from this port, and then steam is generated, collected at the top of the cylinder, and then the steam is emitted from this side. So this steam is then used for power production. Now let us talk about site selection of a nuclear power plant. So number one, obviously this type of plant will require a lot of water for cooling purposes. So it should be located near the river stream or seaside. Next, radioactive waste which is produced by the plant must either be buried deep underground. Either you should create deep pits for that radioactive waste, and then you line those pits with concrete, and then you deposit the waste, and then put a lot of dirt on top of that. So either you do that or you dispose it far from the seashore. So this plant must be located away from populated areas. There are two reasons for that. Number one is health. Obviously, if there are some problems, we do not want these plants to be near populated areas, because as we have seen in the introduction slides, the mishap in Chernobyl caused an entire city to be evacuated. Number two, we have security concerns, because these plants have fuel which can also be used in bombs. So we need secure locations for these plants. These plants can themselves turn into weapons if the chain reaction is not controlled. So security teams are deployed for the plants, and these plants need to be inside the secure location so that any hazard or mishap cannot happen. Obviously, adequate infrastructure must be in place to transport the heavy equipment and technical staff. So, in conclusion, we can say that the plant should be located away from population centers, near a river with adequate arrangements in place for proper waste disposal, vicinity of sea or an isolated area, and infrastructure for logistics. So, number one, you need to locate this plant away from population centers for health and security concerns. Then you have to locate it near a river with adequate arrangements in place for proper waste disposal. So, this site should be near the river, and it should also be suitable for radioactive waste disposal. Either it should be near sea, or it should be in an isolated area where the radioactive waste can be disposed of deep inside the earth, and it cannot infect the surrounding land. And if this surrounding land is used for production of crops, then that will be problematic. So it should be located in an isolated area, and then there should be adequate infrastructure in place for logistics. By logistics, I mean transfer of materials and personnel and all of that stuff.